This is the first lecture for section 11.1 on sequences, and this is the beginning of a new chapter, chapter 11, on sequences and series. And I want to start this chapter with a little bit of motivation before we jump into what's going on with sequences. And the motivation comes from looking at tangent lines. So if you have a nice differentiable function, f of x, then you can approximate the graph by the tangent line. Say at x equals 0, that gives a good approximation to the function near the value x equals 0. And so I would write that by saying that f of x is approximately the formula that you would get for the tangent line, which is f of 0 plus f prime of 0 times x. Okay? And this is our old friend, the linear approximation. Now, one thing that people are interested in, sometimes a linear approximation is usually pretty good, but only for values that are very, very close to x equals 0. And the question is how to get better approximations. And these come from what are called Taylor polynomials. And we'll learn a lot more about these in the coming chapter. But the idea is that f of x is approximately equal to the following polynomial. So you start with the linear approximation. And then you add more terms to get a quadratic approximation. A degree 3 approximation, and so on. You can get an approximation of any degree by adding up terms of this form. Right, so I have a degree k polynomial here where the coefficient of x to the k is 1 over k factorial f to the k. In Britain they call factorial shriek. I'll say what that is in a second. So this is saying that f of x in summation notation is approximately the sum n equals 0 to k of 1 over n factorial. Take the nth derivative evaluated at 0 times x to the n. So here n factorial is 1 times 2 times 3, the product of all the whole numbers from 1 to n. And this is a really, really useful property. For instance, lots of calculators use Taylor polynomials in order to approximate functions that are hard to write down. And the idea is that exact values of sine, for instance, very, very hard to write down. Plugging into a polynomial, that's just multiplication and addition. Calculators can do that really easily and really quickly. Now, that's the first thing. The second thing is that sometimes, right, so you want to take better and better approximations. You probably use more and more terms to do that, and you can take the limit as k goes to infinity. And what you find is that f of x is actually equal to the summation n equals 0 to infinity, 1 over n factorial, nth derivative evaluated at 0 times x to the n. Sometimes. And one of the things that we're going to talk about in this chapter is what this equality even means. What does it mean to add up infinitely many functions, to take a polynomial of infinite degree? And not only that, but what is it good for? And the starting point for a discussion about what this means and what it's good for is the section on sequences. Now, a sequence is nothing but a list of numbers. Usually real numbers. For instance, a sequence that we'll consider for a while here is 1/2, 1/4, 1/8, 1/16, etc. So I'm taking 1 over the powers of 2. And because I have a nice formula for the bits inside that sequence, I can write it in terms of a formula. So in this example, I would have 1 over 2 to the n, where n goes from 1 to infinity. So the numbers that we have on the outside, that's the range of n values. And the formula that we have inside, that's the formula for the numbers in the sequence. And we're going to look at a bunch of examples of this in just a minute. Notice that I can also write this sequence as 1/2 to the n equals 1 to infinity. Right, so the 1 over 2 to the n is the same thing as 1/2 to the n, and so there are frequently lots and lots of ways to write the same sequence. A general sequence has the form curly brackets A1, A2, A3, ... Maybe you list out what an is using a formula and follow it up with ... And in this situation, the terms we use, a sub 1 is the first term, a sub 2 is the second term, a sub 3 is the third term, a sub n is the nth term, right? So the numbers that occur in the sequence are called the terms of the sequence. And this formulation gets tedious to write out, so we'll frequently write these things out like we did above, using a sub n equals 1 to infinity, or just a sub n, if the meaning is clear. So, for example, we could be asked to write out the first 3 terms of a sequence, and the sequence that I want to consider here is -1 to the n times n plus 1 over n plus 2. Okay? And note the change up here. This sequence ranges from n equals 3 to infinity. And that tells me that the starting point is not going to be n equals 1, but it's going to be n equals 3. So the first term here will be when n equals 3, and then if we use a sub n for the general term, this is a sub 3, which is negative 1 to the 3 times 3 plus 1 over 3 plus 2. So just like with function notation, everywhere I see an n, since I'm using n equals 3, I plug in n equals 3. Negative 1 cubed is negative 1, so this one ends up being minus 4/5. The next term when n equals 4, a sub 4 is negative 1 to the 4th times 4 plus 1 over 4 plus 2, so we get positive 5/6. And then the next one, a sub 5, we get negative 1 to the 5th, 5 plus 1 over 5 plus 2, so we have negative 6/7. One thing to notice in this example is that the signs in the sequence alternate. This one goes minus plus minus. They can go, sequences can come with all positives, all negatives, or with alternating signs. Alternating signs are almost always given by powers of negative 1. Right, as we saw in this example, minus 1 to the 5th, minus 1 to the 4th, minus 1 cubed. That was what was giving us the negative signs, or the non-negative signs, in the sequence. Example 1 in the book shows a number of examples like this where you're given a formula for the sequence and you're asked to compute the terms of the sequence. On the other hand, you can be asked to find the formula for the sequence when you're given the initial terms of the sequence. So an example like this. So you're asked to find the formula for the general term of the sequence that starts out with the following numbers: 3/4, minus 6/8, 9/16, minus 12 over 32, positive 15 over 64, etc. So sometimes we list out a bunch of numbers in the sequence instead of just the first 3, so that we can identify a reasonable pattern. So here are the things that I see in the pattern of the numbers. And when you're given fractions, the most helpful thing to do is to usually analyze the numerator, the denominator, and the sign. So the numerator. So the numerators are given by multiples of 3. And I'm disregarding the signs at this point. I'll deal with those separately. So we had 3, 6, 9, 12, and 15. So we have 3 times 1, 3 times 2, 3 times 3, 3 times 4, 3 times 5. So the thing to look for in the patterns is what stays the same in each of the pieces. That's the factor of 3. And what's the thing that changes in each of the sequence? That's the other multiple, 1, 2, 3, 4, 5. Now, what about the denominator? Well, in the denominators we can see powers of 2. Right, so I have 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6. And if you compare, like we did in the previous, in the numerators, the base of 2 is the thing that's staying the same. And what's changing is the exponents 2, 3, 4, 5, and 6. Now those are off ever so slightly from the things that are changing in the numerator, and so I'm going to rewrite this as 2 to the 1 plus 1, 2 to the 2 plus 1, 2 to the 3 plus 1, 2 to the 4 plus 1, and 2 to the 5 plus 1. And the reason to do that is to sync up the blue bits from the numerators with the blue bits from the denominators. So upstairs I'm going to have something of the form 3 times n, where n is the index for the term. Right? So I have multiples of 3 starting with n equals 1, 2, 3, 4, 5. And downstairs I'm going to have powers of 2. I'm going to have 2 to the n plus 1. Right? So if n starts with 1, then my numerators start with 3 times 1. My denominators are 2 to the 1 plus 1 at the starting point. And then the signs that we see, I have plus 1, minus 1, plus 1. Let's line those up with what we have over here. Plus 1, minus 1, plus 1, minus 1, plus 1. And I can write this, right, so this is negative 1 to the 0, negative 1 to the 1, negative 1 to the 2, negative 1 to the 3, negative 1 to the 4, and so we can write those as negative 1 to the n minus 1. That's the same thing as negative 1 to the n plus 1, if you happen to notice that. Either one is perfectly correct. And the end answer is the sign times the fraction with the numerator 3n and the denominator 2 to the n plus 1. And as I said, this can be written out in many different ways. For instance, one could write this as negative 1 to the n minus 1 times 3n over 2 times 2 to the n, which would be negative 1 to the n minus 1 times 3 halves times n over 2 to the n. All sorts of different ways to write the same thing, just like we've seen with functions. You can look at example 2 in the text to see more examples that are like this. The next thing we want to understand is the limit of a sequence. And just like with a function, a limit for a sequence is a trending value for the function. So the limit of a sequence, if it exists, is the trending value of the term an as n gets larger and larger. For example, the sequence that we started with, 1 over 2 to the n, where n equals 1 to infinity. That's the sequence 1/2, 1/4, 1/8, 1/16, and so on. As n gets larger and larger, the value of the term 1 over 2 to the n gets closer and closer to 0. And the notation that we use for this is just like with limits of functions. The limit as n goes to infinity, so that's having n get larger and larger and larger, of the sequence 1 over 2 to the n would equal 0. Right. And this is exactly the same notation as we use for functions when we take their limits at infinity. The only difference here is that n is being used to represent whole numbers instead of arbitrary real numbers. Definition: we say that the limit as n goes to infinity of a sub n is L, here where L is a finite number. This happens if an gets arbitrarily close to L as n grows sufficiently large. So just like we saw in the example up above, you look at what happens to an as n gets larger and larger and larger. And here again, L is a finite number. We also have a notion of what it means for a limit of a sequence to be positive infinity or a limit of a sequence to be negative infinity, but we'll focus here on finite limits. And there's a terminology, so we say that the sequence an converges or is convergent if it has a finite limit, and the sequence diverges if it doesn't have a finite limit. Graphically, limits of sequences are essentially the same as asymptotes for functions. So for instance, if I want to look at an equals 1 over 2 to the n, then when n equals 1, I have 1/2 for the sequence value. N equals 2, I have 1/4. N equals 3, I have 1/8, 1/16, 1/32, and so on. And I see that the trending height for these points is equal to 0. So the limit corresponds to some sort of asymptote. And this is made absolutely clear by the following handy fact. If an is described in terms of a function f evaluated at the numbers n, and if that function has an asymptote, or a limit at infinity, then that sequence has the exact same limit. if you like, a short way to write this would be to write that the limit as n goes to infinity of f of n is the limit as x goes to infinity of f of x, which is of course something that makes perfect sense. So in our example, the limit as n goes to infinity of 1 over 2 to the n is the limit as x goes to infinity of 1 over 2 to the n. And we know exactly what that limit is because the graph of 1 over 2 to the n has a horizontal asymptote as x goes to positive infinity, which is exactly 0. Another example that I want to look at, because we're going to check a limit in 3 different ways, is the next one. Right? So I want to look at the limit of the sequence whose nth term is n squared plus n plus 1 divided by 2n squared plus 5. So method 1 has us rewriting this, so let's call this L. L equals the limit as x goes to infinity of x squared plus x plus 1. So I'm changing my n's to x's, 2x squared plus 5. Now this is a limit of a rational function with the numerator and denominator having the same degree, and I know of at least 3 different ways to evaluate this limit. We know that the limit is 1/2, and I can compute that either by using L'Hopital's rule, or by multiplying top and bottom by 1 over x squared, or by simply knowing that when I have a rational function where the numerator and denominator have the same degree, then the limit is the ratio of the leading coefficients. Now, the nice thing about the second method is that, I should say the second method here of computing that limit with the x's, is that I can exactly use the same limit technique without changing to x's. So I can write my L as the limit n goes to infinity, n squared plus n plus 1, 2n squared plus 5, and multiply top and bottom by 1 over n squared. And again, the reason that I choose n squared, as we did with x squared, is this is the largest power of x occurring in the denominator. And when I simplify this, we get the limit as n goes to infinity of, I have to multiply that 1 over n squared all the way through the numerator, and when I do that and cancel terms, I have 1 plus 1 over n plus 1 over n squared, and then my denominator will be 2 plus 5 over n squared. And as n goes to infinity, 1 over n goes to 0, 1 over n squared goes to 0, and 5 over n squared goes to 0 as well. So the limit that we get using this technique is the same. We get 1/2. Okay. Now, this technique uses basic facts about limits of sequences that come from the old limit laws that we learned last semester for functions. So for instance, we have that the limit of the sum is the sum of the limits. Now this assumes that each of these sequences is convergent. Okay. So let's write these limit laws out explicitly on the next page. So we're going to assume that the limit as n goes to infinity of an is L, that's a convergent sequence, and the same thing for Bn. Have that be a convergent sequence with limit m. And we're going to let C be a constant. Then the limit as n goes to infinity of an plus bn is L plus m. So this says two things. It says that the sequence an plus bn is convergent because the individual sequences an and bn were both convergent, and moreover that the limit of that sum is the sum of the limits. And similarly for differences, constant multiples or products quotients of course here we have to assume that the thing that we're dividing by m is non-zero. Notice that this makes it automatically so that the sequence an over bn is defined at least for all but finitely many values of n. I can do pth powers and I can also do powers. So let's do that over here. So the limit as n goes to infinity of r to the n, right? So here r is some fixed number and I'm raising it to a power, and this will sometimes have a limit. So this limit will be 0 if r is between plus or minus 1. It will be 1 if r equals 1. Of course, the powers of 1 are just 1. And these are the only conditions under which that sequence converges. So the sequence r to the n diverges whenever r is less than or equal to -1 or r is strictly greater than 1. Okay, so these are the limit laws that we have for combining limits together and the basic features of the limits of powers. You can see examples of this, more examples in the text in examples 4 through 7. The basic idea with limits of sequences is that if there's a rule for limits of functions, then there's also a rule for limits of sequences. So for instance, we have a squeeze theorem. And the squeeze theorem says that if an less than or equal to bn less than or equal to cn for all n greater than or equal to some fixed value n naught, and the sequence an has a limit L and that is the same as the limit of the right-hand sequence. So I'm asking that this sequence Bn is pinched in between two convergent sequences that have the same limit L, and then the conclusion is that sequence Bn is also convergent and has the same limit. So let's look at an example of that. I want us to figure out whether or not the sequence, the following sequence, 3 to the n over n factorial, as n goes from 1 to infinity, is convergent. And the idea with this is that we're going to write out some terms and look for a pattern, and we're going to be able to apply the squeeze theorem. So we're going to write out some terms. So when n equals 1, we have 3 over 1. Right? 1 factorial is 1. When n equals 2, we have 3 squared, so 3 times 3 over 1 times 2. That's 2 factorial. When n equals 3, we have 3 times 3 times 3 over 1 times 2 times 3. And I'm going to write out a few more terms like this. Right, so the general term of this sequence has n multiples of 3 in the numerator and the product of the numbers 1 through n in the denominator. And here's the thing to note about the terms of this sequence. So this third term, I can cancel the 3's, and I end up with 3 times 3 over 1 times 2. Which is the same as the second term. In the fourth term, I can cancel those 3's, but then I'm left with 3/4 as a leftover. So I'm going to write that as 3 times 3 over 1 times 2 times 3/4. The next one, when I cancel the 3's, I have my 3 times 3 over 1 times 2 times 3/4, that same 3/4, and then also a 3/5. Now notice this is when n equals 5, and here I'm going to get a 5 that's very interesting right here. And the point is that this number, so 3/4 is less than 1, so this is 3 times 3 over 1 times 2 times 3/5, strictly less than that. So notice the pattern that I have started here. Here I have this number times this number, which is smaller than 1. I have the same number times this number, smaller than 1, where the denominator corresponds to my n value. And over here, I can rewrite this one, 3 times 3 over 1 times 2 times 3/4, 3/5, all the way up to 3 over n. And if I collect all of these numbers in parentheses together, they give me something less than 1. So I end up with something that's less than 3 times 3 over 1 times 2 times 3 over n. So the conclusion, which I'll write over here on the left, is that my sequence 3 to the n over n factorial is less than 3 times 3 over 1 times 2 times 3 over n, and it's of course greater than 0. And the key with this sequence is that it converges to 0, because I have a constant out front, that's 9/2, and I have 3 over n, which as n gets larger and larger and larger, dividing by n gives me something closer and closer to 0. The limit of this constant sequence is also 0, so the squeeze theorem tells me that the limit as n goes to infinity of that sequence that I started with, 3 to the n over n factorial, is 0 as well. So you can see the convenience of the squeeze theorem is to take a complicated sequence and turn it into, or compare it to, two simpler sequences by noticing the pattern in the numbers that occur. Another example of the squeeze theorem you can see in example number 10 in the text. Two more useful facts for us to consider in this lecture. The first of these has to do with absolute values. Is that if the sequence of absolute values converges to 0, so that is the limit as n goes to infinity of the absolute value of an, if that limit is 0, then the limit as n goes to infinity of the original sequence without the absolute values is also 0. And you can see that being incredibly useful, say, with the next example, where I want to compute the limit as n goes to infinity of -1 to the n squared plus 3n plus 1 times 3 to the n over n factorial. And I claim that this is equal to 0, and that's because the limit we computed previously is exactly the limit of the absolute values. So easy, easy, easy. You don't have to worry about it at all. And you can see another example of this in the text, in example number 8. Last useful fact for us to consider has to do with continuous functions. And this is going to make it really nice for us to combine sequences together. It says that if the limit as n goes to infinity of an equals L, so if I start with a nice convergent series sequence, and I have a continuous function f of x, then I can modify that sequence that I started with and consider the limit as n goes to infinity, not of an, but of f of an. And the conclusion is that this will be f of L. Now, it may not be particularly nice to remember it in this form. The form I like to remember it is that the limit as n goes to infinity of f of an is the same thing as f of the limit as n goes to infinity of an. And again, this assumes that f is continuous. So for example, the last example for this lecture, if I want to compute for some reason the limit as n goes to infinity of the arctangent of the sequence -1 to the n squared plus 3n plus 1 times 3 to the n over n factorial, that's going to be the same thing as the arctan of the limit of the sequence -1 to the n squared plus 3n plus 1, 3 to the n over n factorial, this limit as n goes to infinity. This limit we already computed, or at least one like it, is equal to 0. So we end up with the full limit being arctan of 0, which is 0. And you can see another example like this in the text in example number 9. So this is the end of the first part of the lecture on section 11.1 on sequences.